Erin and Katora. I'm going to do that class that we couldn't do. I had to get a new account and everything in order to get this Quiz IQ to work. So I'm going to quickly do this lesson. We're going to do section 1.4. I already gave you your homework for this. This one's called Shifting, Reflecting, and Stretching. Graphs. Sounds fun, right? Okay, so we're going to start with, you have graphs. Now, one thing you have to do is you have to memorize what I call the parent function or the base function for various graphs. So if you have a graph such as this one, and we're going to write it in function notation. So I'm going to write f of x equals x. That's just some value. It's going to be a straight line, or you could say f of x. Well, let's just start with that. That's the parent function for a straight line. This one would be, if you were to graph it, would be a straight line. So it would look like if we had a graph, I'm not gonna do the whole graph thing right now. I was before when it didn't work, but I'm gonna go a little quicker here. This would be a straight line. The slope, you can see there's no plus anything on there, so it's not going to have a y-intercept. The y-intercept is just going to be 0. It has a y-intercept, but it's going to be 0. So that's what that parent function looks like. You have to memorize it. It's a linear equation. The highest degree is 1. It's a straight line. Another parent function is f of x equals the absolute value of x. So what would that one look like? I can just stick on the same graph here, I guess. So we'll just change our color. We'll call this one the orange function right here. It's going to look like a V. Absolute values look like V's, like this with arrows on each end. That's because if you put a 1 in, you're going to get a 1 out. If you put a 2 in, you get a 2 out in an absolute value function. If I put a -1, I get a +1. If I put a -2, I get a +2. So memorize, absolute value functions always look like V's. And as you can see on our lesson topic, we're shifting, reflecting, and stretching. So I should get rid of that orange color up there. So we're going to be doing some crazy things with our graphs. So let's do our next one. We have f of x equals the square root of x. Now what would that one look like? So we'll make this one another color. Let's go with bright green. So bright green, let's see what that would look like. It would start at 0, 0. If you put a 0 in for x, square root of 0 is 0, you're going to 0 out. If I put a 1 in, I'm going to get a 1 out. If I put a 4 in, I'm going to get a 2 out. So if I put a 9 in, I'm going to get a 3 out. So it's a very gradual increase. And so absolute value functions just kind of look like this shape. And I can just draw a little picture off of the graph what it looks like. It looks like this. The absolute value function looks like this, and of course we know what a straight line function looks like. So let's do the next one. And as I said, I mean, you can kind of figure these out without memorizing them, but it's easier just to memorize them. This one is a parabola. A parabola looks like this as the parent function. So if I put it on the graph, it'd be purpley up here. A parabola gets bigger faster. It's the opposite of the square root function, which gets bigger slowly. This one gets bigger faster because it's exponential. So if you put a 2 in, you're going to get a 4. If you put a 3 in, you get a 9. They're always going to be positive because when you put a -3 and square it, it also becomes positive on the y value. And then the last parent function that this book talks about is the cubic function. And it's going to look like this. F of x equals x cubed. That's going to be, whoops, I gotta get a color for it. Let's see what color did I use. We don't have a blue. So it's going to look like this. That's your cubic function. That's your parent cubic function. So it's going to go, all these are starting through 0, 0 until we do what it says above, shift, reflect, and stretch. So that's the basics. Now we're going to shift, stretch, and reflect these. So I'm going to have to go to another board to do this, unfortunately. So here we go, new board. First thing we're going to do is vertical and horizontal shifts. So hopefully you wrote down from the last whiteboard the parent function. So first one we're going to do is if you have, we're going to go with h of x. If you have h of x equals x squared plus 2, for example. Now you know, because you know your parent functions now, that this is going to be a parabola. So it's going to look like a parabola. Now we have something added on to the end, and that's a plus 2 added on to the end, which means when something is added on to the end, it means it's going to be a vertical shift, whatever this is. They have, they show this below in your book. They'll say something like h of x equals f of x plus c, and that would be a vertical shift. Vertical shift, if it's a plus c, it's going to be upward. If it's going to be a f of x minus c, it's going to be a vertical shift downward. So what this would look like on the graph is if you had your graph here, hopefully this is showing up in the window that I chose, your parent function would look like this, right? But since we're adding the plus 2, it's going to look like, it's going to go up 2, it's going to look like this. So we did plus 2, so we just moved the whole thing up vertically 2. Now, the other case for this, we're going to work with the parabola function here because the parabola is, you know, kind of our friend. So if we had the function g of x equals, hopefully my house isn't too loud for us here, x minus 2 squared, you'll notice that the minus 2 is inside of this squared part. So instead of it moving up and down, this one's going to move to the left or to the right, depending if it's minus 2 or plus 2. So if we were to graph this on, we'll just go up to that graph up there. Make this one orange. Orange is a great color for this. This time we're going to go whatever it is. If it's inside, if it's negative, we go to the right. If it's positive, we go to the left. It's kind of opposite of what you would think. But if you added the positive 2, it would bring us back to 0. So I'm just going to take this whole parabola and I'm going to move it over 2. It's not going to go up or down. It's just going to look like this. So we shifted it to the right too. And the little rule for this is if you have h of x and if you have f of x minus c, or you could say plus or minus depending on which way you're going to do it, it would be a horizontal shift and it would just depend. If it's minus c, it's going to go to the right, and a plus c, it's going to go to the left. So if it's a minus, see how it's inside the function? Up here, it's outside of the function. Down here, it's inside of the function, so it's going to shift left to right. Now we're going to do that with every function, whether it's cubic, whether it's absolute value. If you're adding or subtracting anything on after the function, it goes up and down. If you add it inside of the function, it's going to go left or right. So let's try a couple examples of these. All right, so we have our first example is we have g of x equals x squared minus 1. Easy one. So we have our graph, yx. Our parent function would start at 0, 0, right? But this is minus 1. It's outside of the squared, so it's going to go down 1. And we're just going to shift it down. Whoops, I missed it though. Have to hit that point and up, and that's how you would draw it. So we're sketching them. It's not exact, but we're sketching it. The next one is h of x. They really want you to compare this with the parent function. So let's just put the parent function here in purple. This is our parent function. All right. So the next one is h of x. Oops, having trouble changing colors. is x minus 1 squared. So this one is going, since it's negative, it's going to go 1 to the right. We'll just go with some red. 1 to the right, like that. And we're just going to go around, and that's how that one's going to look. This is our red function. And let's just do one more real quick. We'll do green. I'll just write the whole thing in green. H of x equals x plus 2. Oops, they're being very tricky. Cubed. Ooh. I didn't realize we were doing cube. I can't even read the book. Let's just stick with squared since I started with squared. Plus 1. So this one's a double whammy. It's a plus, so we're going to move 2 to the left. It's opposite of what you think. Remember that. And 1 up. 1 up. So it's going to be right here. So our parabola is just going to move 2 to the left and 1 up. These are kind of fun. So that's about it for moving your graphs. The next thing is we're going to talk about reflecting our graphs. So reflecting is like, let's just go back up here to this purple parabola, which is the parent function. And I'm going to reflect it over the x-axis. So I'll just pick this green. We're going to reflect it over the x-axis. Means it's going to flip this way, and we reflected it over the x-axis. So if you're going to reflect a graph, if you have the function h of x, to reflect it over the x-axis, the negative is going to be outside of the function f of x. This is going to reflect it over x-axis. Now, that's when it's outside of the function. So if I wanted to put like this darker green one, if I want to reflect that, that's going to look like this. G of x equals negative x squared. Or if I wanted to flip this guy right here, it would look like this. G of x equals negative x plus 2 squared plus 1. So anytime I'm going to reflect it over the x-axis this way, the negative is going to live outside of the parentheses. Yeah. We can also reflect a graph over the y-axis. Now, if you reflected a parabola over the y-axis, take, for instance, this white one right here, it would look exactly the same because it's symmetrical. But some shapes wouldn't work like that. Like if you had a cubic function and you flipped it over the y-axis, it would then look like this, right? So, just saying. So if you have the function h of x, and it would be, and you had f of negative x, it would reflect it over the y-axis. So what would that look like? I think I have a little bit more space on these whiteboards that I'm using. So if you had something like, let's see if I can find an example. Okay, let's look at a couple examples of this. Let's just move right to the example section. We have, it says, compare the graph of each function with the graph of f of x. Oops. F of x. I have to go plug up my computer. Hold on 1 second. All right, sorry about that. My battery power went down so fast. So if we have f of x, this is the function we're comparing to, the square root of x. Now, if you remember from the first screen, this is a square root function. So we're going to do some crazy things with this square root function. If you have a graphing calculator, you can try all these on your calculator and see what they do. So if I have g of x equals the square root negative square root of x, that's outside of the function. That's outside of the square root of x. So that one is going to reflect over the x-axis because it's outside. You have to memorize. Even math has some memorization to it. So if we had our coordinate system. And we have the square root of x. Remember, this is going to be, I made it a little steep. Let me just fix that, a little too steep. And I can't quite get that right. And we're doing this one right here. Let's do this light pale color. So if you put the negative in front, it's going to flip over the x-axis like this. So that's if it's outside. Let's look at another one. I'm just going to do it in the color. What haven't I used before? Yellow. Let's see how that looks. So if we have the next one, h of x equals the square root of negative x, that's going to, see how it's inside like this one? So it's going to flip over the y-axis. So that means it's going to go this direction because it flipped over. It should be symmetrical, the flip. So that's what that's going to look like. Now let's do a really complicated one. Let's just pick another color, bright blue. Here's the most complicated one. K of x equals negative square root of x plus 2. Now, the negative is outside of the function, so this one's going to flip over the x-axis. So if I make this function, we have our parent function, this means it's going to move 2 to the left because it's a positive 2. So this function, this white one, it's going to move us 2 to the left. It's going to go over here. And then it's going to flip. So if I just did it 2 to the left, it would look like this, right? But it's going to flip over the x-axis. So this function, the blue one, is going to look like this. It did a double thing. It moved to the left 2 because it's a plus 2. And then it flipped over the x-axis. So very, very tricky. One more thing, if you remember from the beginning of our lesson, we said we're going to do shifting, which we did. That's the left and right. Reflecting, that's over the x-axis and the y-axis. You can also flip over the a vertical line, but it doesn't look like they're going to teach us that yet. And that was our reflecting. Now we're going to stretch our graphs. So let's move on to stretching. We'll see how much we can get in this week. So this one's called, we're going to compare the same thing. Let's just do, I'll just call this example 3. All right, hopefully our next online class isn't quite the disaster that last one was. 3 absolute value of x, and they have 2 of them. They have g of x equals 1/3 absolute value of x. And we're going to compare this with our absolute value function, which looks like this. Remember, this is our parent absolute value function. But we changed the number that's in front of there. So in the book it says horizontal shifts and vertical shifts and reflections are called rigid transformations because the basic shape of the graph is unchanged. These transformations change only the position of the graph in the coordinate plane. Non-rigid, that's what this one's going to be called, non-rigid transformations are those that cause a distortion or change in shape to the original graph. So we're going to, it says in the book, a change in the shape of the rigid graph. For instance, a non-rigid transformation of the graph y equals f of x is represented by, and they're going to say the non-rigid looks like this, y equals, remember we had a c on both of those? This time the c is in front, c of f, c times f of x. So that's what we have here. These are our c's. One's going to make it wider and one's going to make it steeper. So it also says each y value is multiplied by c where the transformation is a vertical stretch. So if c is greater than 1, it's called a vertical stretch. And when c is less than 1, it is called a horizontal stretch. Now, if it's equal to 1, it's the same graph, so don't ask that question. Horizontal stretch. So, and if it's inside, we have a horizontal shrink and a horizontal stretch. So if it's inside of the function, let's see, how did they write this? So if you have y equals f of cx, that's going to cause a horizontal shrink and a horizontal stretch. Yikes. Okay, so you don't have to do these too often, but if it's going to be a one outside, it's going to be a vertical stretch. So we have our parent function up here. Let's just do the first one. We'll call this A, this one called A, and this one called B. So if you have your parent function, I'll just draw this a little bit bigger, y, x, and we have the horizontal stretch. It's just going to get wide. It's going to get more narrow. That's why it's called a vertical stretch. Let me just show you why that's true. So, whoops. First of all, you have to hit your, I'm trying to go too fast, I think, because I know these videos can get really, really boring if they drag on and on and on like this one is. So this function would be, if this is a absolute value function, if you put a 1 in, you get a 1 out, right? 1 in, negative 1 in, you get a positive 1 out. If you put a 2 in, you get a 2 out. If you put a negative 2 in, you get a negative 2 out. Let's just see with part A, if you put a 1 in, what are you going to get out? This time, you're going to get out a 3. So you would get a 1, 1, 2, 3. Whoops, should have been a little higher. If you put a 2 in, you're going to get a 6 out. If you put a 2 right here, you would get 2 times 3 is 6. So you get 1, 2, 3, 4, 5, 6. So you can see how it's vertically stretched. It's going to be symmetrical over here. So you can see it's going to be a more narrow graph. And when you have the 1/3, it's going to get fatter, because when you put a 1 in, you're going to get a 1/3 out. So you get 1 and you get a 1/3 out like this. And if you put a 2 in, you're going to get, or a 1/3, yeah, if you put I'm in the wrong one. If you put a 2 in, you're going to get 2/3. So let's just put a 3 in because it's easier. If you put a 3 in, you're going to get a 1 out. So 3, 1. And you can see how this graph is going to be much fatter like this, and that's called a horizontal stretch. Did I mean to write horizontal? It should have been I wrote this wrong. Sorry guys. This is called a vertical shrink. And you can see why it shrunk. This one's like, it's lower to the ground. It's a vertical shrink, and this is called a vertical stretch. So we'll try some of those. That's basically it for the lesson that I gave you. So we'll just end with that, and we'll go over all this homework on Thursday, and then we're going to do, I did start with combinations of functions, so let's just do that. We're here, and I did give you that homework. So this is 1.5. I'm just making this one video because I've had so much trouble with WizIQ that I'm afraid to exit and try it again right now. This is 1.5, and it's holding up okay for me. Combinations of functions. We've done this in Saxon. So if you have f of x plus g of x, and they tell you ahead of time that f of x is 2x minus 3, and g of x is equal to x squared minus 1, if it asks you to add them together, you simply add the functions together, and you're going to get negative 4, and this would be x squared, negative x squared plus 2x. And that's all you do, is you're just going to add those together. This is a 4. So if you're adding them, you just add them together. If you're going to subtract them, f of x minus g of x, I'm going to do this on the side here so it's not so messy. So f of x is 2x minus 3, and we're going to subtract, because all of a sudden it's starting to write funny. We're going to subtract, I think this was supposed to be equals, so it should have been a positive. All of a sudden it's not writing very well. So 2x minus 3 minus x squared minus 1. So this time we're subtracting the two functions, so you're going to get 2x minus 3 minus x squared plus 1. So that's going to give you negative x squared plus 2x minus 2. So if you're going to do that, if you're going to multiply the two functions, if we have f of x times g of x, you just multiply them. But you're going to have to use FOIL for this because it's 2x minus 3 times x squared minus 1. And you would use FOIL for that, first, outer, inner, last. And you're going to get 2x cubed minus 3x squared minus 2x plus 3. And then the final one they're going to have is they're going to have f of x divided by, I must have slow internet or something. So we're going to get 2x minus 3 divided by x squared minus 1. And the only thing, you just leave it like that because you can't really do long division with that because the lower degree is on the bottom. So you just have to make sure you check out the domain. And we've talked about domains. This can't be 0. So x cannot equal. If you put a 1 in there or a negative 1, you're going to get 0. So you have to say your domain can't equal 1 or negative 1. So that's about all for that. And then when we come back on Thursday, we'll do some compositions of functions. So that is it for 1.4 and 1.5a.